So I'm going to show you two sets. I'm going to use string patterns to describe these two sets. So I'm going to call this L1 is, the set 0 to the n, 1 to the m, where n is greater or equal to 0, m is greater or equal to 0. Okay, so some number of zeros followed by some number of ones. And it could be 0, 0, then it could be 0, 1. So epsilon is also in this set. Okay, L2 is equal to 0 to the n, 1 to the n. Okay, so this is where n is greater or equal to 0. Okay. Okay, so what is this? So this is just some number of zeros followed by some number of ones. So, exercise. Okay. Give regular expressions that describe these languages. 1. Give regular expressions. And 2. Give recursive definitions, recursive sets. Give recursive definitions for these languages. Okay. Okay. And turns out that these languages look very similar. So they're very similar looking. So these languages look very similar. Look, it's a bunch of zeros followed by a bunch of ones. Okay, a bunch of zeros followed by, in this case, an equal number of ones. They look very similar. Strings of zeros followed by ones. It turns out that these two languages are very different. Okay, very different. So even though they look very similar, they are very different languages. And I could ask you, well, it turns out that one of them is much more complex than the other. And, you can pause the video and try to guess which one of these is more complex. Okay. And, I'll give you so I'll pause the video, 1, 2, 3, 4, 5. If you're coming back just for the ride, you might have thought, oh, this is more complex because it involves two variables, n and m. No. Turns out that this is way more complex, even though it involves just one variable. Okay. And that's because, here n and m are arbitrary. Okay, so it's just a bunch of zeros followed by a bunch of ones. Here, somehow this language embeds the notion of equality. So n must equal m. So m must equal n. That's why it's 1, 0 to the n, 1 to the n. So this language is more complex, but we have no idea what that even means. Okay, what does it mean that the language is more complex? Okay, so when you try to give regular expressions for both of these, you'll find that for the more complex language, it's going to be very hard to come up with a regular expression. Just like it's very hard to come up with a regular expression for the palindromes. And when I say very hard, I mean very hard. I mean impossible. Okay? And you might say, what? There's no regular expression for this? Yes, for this equality. There's no regular expression. Is there no regular expression for palindromes? Yes, there's no regular expression. And we'll prove it later. Okay? But recursive definitions, no problem. You can come up with recursive definitions for both of these. Okay? And that suggests that, in some sense, if you view regular expressions as a nice, convenient, simple way to describe languages, then this is simple, this is complex. Okay? If you view recursive definitions as a complex way to define languages, complex, very powerful, then it's powerful enough to describe both. Okay? But, there are two messages here. So we won't get into those details yet, but there are two messages here. Okay? Well, the first is, what is the complexity of a language? What is the complexity of a language? Okay. So we're going to have to sort of try to define that. And why do we care? Why do we care? Okay. And so the why do we care is actually much easier to answer. Okay. Why do we care is, well, remember where languages came from. Languages came from computing problems. Okay. And, computing problem was this vague sort of notion of you feed in an input and you get some output. Well, now we pinned it down. A computing problem is a decision problem. Okay, so a computing problem is a decision problem. Okay. Well, but then what is a decision problem? A decision problem is just a language. This is just a language, the yes set, the language, i.e. the yes set. Okay, so that's what a decision problem is. Okay. And we're on our way towards trying to understand which kinds of computing problems are hard, i.e., impossible, and which kind of computing problems are easy, i.e. possible. Okay. And along the way, we're going to see a whole spectrum of problems going from easy to sort of slightly harder, and then to impossible. Okay. And we want to sort of be able to quantify how hard is a computing problem, and it boils down to basically saying how hard or complex is the language, is the yes set that is associated with that decision problem. So if we have a way of, describing or defining or quantifying the complexity of a language, then we have a way of quantifying how hard a computing problem is. Okay? And so let me give you a sort of taste for what we're going to do next time. So in order to for the rest of this class, in order to define the complexity of a language, that brings us to models of computing. Okay? So let's now talk about the complexity of a language.